Happy viewers. Myself, Dr. J. Abdulbari, working as Associate Professor in the Department of Civil Engineering of K.S.Rangasamy College of Technology. Today, we are going to discuss an important topic in structural analysis, namely the theorem of three moments, also known as wraparound theorems. This theorem is a classical analytical method used mainly for the analysis of continuous beam, which are statically indeterminate structures. Understanding this theorem will help you to appreciate how compatibility conditions are used to solve indeterminate problems and will also strengthen your basic before moving to softer based analysis. So the content we are going to look into this are understanding the indeterminacy, types of structures, theorem of three moments, and the practical applications. That's real world engineering solutions. Before going into the theorem, let us first understand the indeterminacy. A structure is said to be statically indeterminate when the number of unknown reactions exceeds the number of available equilibrium equations. In such a case, equilibrium equations alone are not sufficient. When then introduced the compatibility conditions, which ensures that the structures deformed in a physically acceptable manner. The degree of statically indeterminacy is calculated with the help of the formula, that is dSi equal to small r minus 3m plus s, where r is the number of the reaction components, m is the number of the members, and s is the number of static equilibrium equations. This concept is essential because the theorem of three moment is applicable only to the statically indeterminate structures. Next, kinetic indeterminacy. Now let us briefly look at the kinematic indeterminacy. Kinematic indeterminacy refers to the number of indeterminate displacement components or degrees of freedoms, which is required to describe the deformed shape of the structures. Unlike static indeterminacy, which depends on the forces, kinematic indeterminacy depends on joint constraints and support conditions. This concept is extremely important in stiffness methods, point element analysis. In simple terms, the kinematic indeterminacy tells us how many unknown displacements of the structures will have, which directly controls the size of the stiffness matrix in numerical analysis. The structural systems overview, that is the types of the structural systems. Now let us review the main types of the structural systems we deals with, that is beam. Beams are the horizontal members subjected to transverse the loads. When the beams extends over more than two supports, they become the continuous beams, and these are called as statically indeterminates. Trusses. Trusses consist of straight members connected at the joints. In ideal truss analysis, members carry only axial forces and loads are applied at the joints. Frames. Frames consist of the beams and columns connected through the rigid joints. They resist bending, shear, and axial force simultaneously, making them more complex and often indeterminate. The three moment theorem is specifically applicable to the continuous beams, which falls under the beam category. Determining the indeterminacy. Now let us see how indeterminacy is calculated for the different structures. For beams, the degree of static indeterminacy is calculated as capital R minus 3, where R is the number of the reaction components. For a simply supported beam, capital R is 3, hence it is determinate. For a continuous beam with multiple supports, have R capital, that is capital R is greater than 3, making it indeterminate. For trusses, the degree of static indeterminacy is calculated as m plus r minus 2j. For the rigid frames, degree of indeterminacy is calculated as 3m plus r minus 3j, where m is the members, r is the reactions, j is the joints. For trusses, this accounts for the two equilibrium equations per joints in two-dimensional analysis. For rigid frames, the degree of indeterminacy guides the selection of the appropriate analysis method. Understanding indeterminacy helps us to choose the correct method of analysis, such as three moment theorem for the continuous beams. Now we come to the core topic, the theorem of three moments. The theorem was developed by the Benoit Clapeyron in the year of 1857. It established a relationship between the bending moments at three consecutive supports of the continuous beam. The theorem is based on elastic behavior of material, small deflections, constant flexural rigidity unless specified otherwise. The major advantages of the theorem is that it converts the statically indeterminate problems into a set of soluble linear equations using compatibility conditions. The three moment equations. The three moment equations relates the moments at three consecutive supports, usually denoted as m1 plus m2 and m3. The general form of the equation is MAL1 plus 2MB into L1 plus L2 plus MC into L2 will be equal to minus 6A x1 bar by L1 minus 6A2 x2 bar by L2. These equations accounts for the span lengths, loading conditions and flexural rigidity. By writing one equations for each set of three consecutive supports, we can form the system of equations and solve for the unknown support moments. Once the support moments are known, the entire beam can be analyzed using the basic equilibrium equations. So the variables which has been defined in these equations are MA, MB and MC are the bending moments at the consecutive supports A, B and C. L1 and L2 are the span lengths between the supports, and A1 and A2 are the area under the bending moment diagrams, that is M divided by EI, and x1 bar and x2 bar are the centroidal distance from the left supports. So the key assumptions to be used in these three moment equations is small deflections and linear elastic behavior, and we'll have the constant flexural rigidity, that is EI, and two-dimensional plane frame analysis can be found out, and there is no settlement at the supports. The solution methodology. The solution procedure using the three moment theorem follows four systematic steps. First one is identifying the system, that is to determine the number of spans and the degree of indeterminacy. Second, apply the theorem, that is write the three moment equations for each set of three supports. And third, solve the equations, that is solve the simultaneous equations to obtain the support moments. And fourth, complete the analysis, that is calculate the reactions and draw the shear force bending moment diagrams. This step-by-step approach makes the theorem ideal for hand calculations and academic learning. Coming across to the engineering applications, now let we look into some practical applications. Bridge designs. Continuous girder bridges commonly use these theorems in preliminary analysis to understand moment distribution and optimize material usage. Building floor systems. Multiple span beams in buildings are analyzed to control the deflections and ensure structural safeties. Modern software validations. Although we now use advanced softwares, classical methods like three moment theorems helps engineers verify the results and improve engineering judgment. Understanding theory ensures we don't blindly trust the software outputs.